Alrighty, thank you much. Have you ever been paged late at night to troubleshoot a production issue, only to find that someone made a mistake earlier when deploying a change and missed one server? Have you ever made a change for troubleshooting purposes and someone else got paged because you forgot to change it back? Have you ever had a coworker quit and you and your team discovered later that you have no idea how they configured something? Issues like these and more can be prevented or automatically remediated by integrating the principles of infrastructure as code, as well as tooling such as HashiCorp Packer or HashiCorp Terraform into your environment. Hi, I'm Troy Lindsay, and today we're going to start off with an overview of Terraform. Then we're going to go over what we're going to build today. After that, we'll deploy our hybrid solution with Terraform that weaves VMware and AWS resources together, and we'll take a look at the code. All of the code for the examples have been published in a GitHub repository, and I'll share a link for it at the end. If you're worried that you have to be if you have to have a computer science degree to understand this stuff, don't be. If you can read and update config files and shell scripts, then you can learn this too. So what is Terraform? Terraform is an open source infrastructure as code tool that automates the provisioning of a wide variety of resources in a wide variety of environments. You can run it from most major operating systems, such as Windows, Mac OS, and Linux. With this, you can describe a VM, workload, or even your entire environment in code, and then rapidly deploy it. Terraform isn't only for deploying VMs and Amazon EC2 instances, though. You can deploy and manage all sorts of resources, such as DRS anti-affinity rules, AWS Lambda functions, vSphere licenses, Amazon RDS databases, and so much more. Here are some other key benefits. Terraform is idempotent. This weird little word simply means that it works correctly no matter how many times you run it. For example, if you write a config file for deploying 10 VMs, Terraform will only deploy a total of 10 VMs, whether you run it once or 1,000,000 times. Every subsequent run will make sure that all 10 VMs exist and are in the desired state. And if so, it completes without making any changes. This is key to trusting your automation. Next, Terraform is declarative. This means that you only have to describe your resources that you want to deploy and how you want them configured. Terraform will take this and generate an execution plan to achieve your desired end state. You don't have to specify all the necessary steps and procedures involved with building it. Just describe what you want, and Terraform will figure it out for you. Continuing the previous example, if you delete one of your VMs and then run Terraform again, it will deploy a new VM to replace the deleted one to get you back to the desired state of 10 VMs. If you increase the desired quantity in your config file from 10 to 15 VMs and then run Terraform again, it'll deploy 5 more VMs without any additional instructions. If you then reduce the quantity to 5 VMs and run Terraform again, it'll automatically pick 10 VMs to power off and delete from disk. You can't do this kind of thing with most configuration management tools or scripts without code changes. Terraform will automatically map dependencies between resources when it builds the execution plan. This ensures that each resource is deployed in the proper order to achieve the desired end state, even if they aren't described in that order in the code. This means that if you use the output of one resource as an input for another, Terraform will automatically identify that dependency and wait to deploy the second resource until the output of the first resource is available. For example, if you write a Terraform config file that describes a new resource pool and a VM that will be deployed in that resource pool, Terraform will not attempt to deploy your new VM until your resource pool is ready to go. Terraform is self-documenting. Everything managed by Terraform is described in detail in the code and state, so you can tell what's deployed at any given time and how the resources interact. When your documentation has to be accurate in order to deploy your changes, since your documentation is your code, your environment starts getting easier to understand, troubleshoot, and manage. This is especially valuable when you need to help auditors understand how your environment works and how it's secured, such as when your company wants to achieve or renew a compliance certification like PCI. When your infrastructure is defined in code, then it's easier to review with your peers and compare changes. This will help you improve uptime and reduce failure rates. You can also build automated tests to help you move even faster and reduce the risk of human error. Terraform code is reusable. There aren't a ton of differences in Terraform between deploying a Windows VM from a VM template and a Linux VM. When you need to design a new workload, you can usually start by copying an existing code block, such as in the example code that we'll look at today, and then iterating on it. Automated systems can deploy resources faster than humans. They're consistent and repeatable, and they're not prone to human error. If you've ever written complex and detailed deployment instructions for someone else, only to have them mess it up, then you'll truly appreciate the accuracy aspect. And last, skills like these are in demand right now, so invest in yourself by learning them, because many organizations have already started realizing the benefits and are looking for more people who understand them. So let's take a look at what we're going to build today. Here's what our end state will look like once everything is deployed. We're going to deploy an AWS File Gateway VM and a MySQL Server VM from existing VM templates in a VMware Cloud on AWS Software Defined Data Center, or SDDC. Even though we're deploying this in a SDDC for the demo today, you should be able to use the example code in your on-premises vSphere environment with few to no changes necessary. The key difference is that you'd replace the AWS private link with either a AWS Direct Connect or a site-to-site VPN tunnel for providing the private network connectivity between the environments. Of note, MySQL Server VM template was built earlier today with HashiCorp Packer. And if you're interested in learning more about this, check out the video and GitHub repository for my previous session, CODE4238, Building VM Templates Programmatically with Packer. If you're not familiar with VMware Cloud on AWS, it's VMware's compute, storage, and network virtualization stack, so vSphere, vSAN, and NSXT, running on top of Amazon EC2 bare metal hardware and delivered as a service. The SDDC we're using today is deployed in the US East 1A availability zone, or AZ. This AZ is located in the Northern Virginia region in the US, which is known as US East 1. If you're not familiar with the concept of an AZ, it's one or more data centers with redundant and separate power and fully isolated from the other AZs in the region. The white box on the right here represents my AWS account. And the orange box on the left represents my VMware Cloud on AWS account. Each customer's SDDC is deployed in a dedicated AWS account that is owned and operated by VMware. One common misconception is that the EC2 instances running ESXi will be deployed in your account and that you'll see them in the AWS Management Console. This is not the case. The virtualization stack is deployed in the VMware Managed account. Next, the two AWS accounts have private connectivity between each other through AWS Private Link. High-speed, low-latency, private connectivity provides you with interesting opportunities to extend your environment and save money. For example, the SDDC's vSAN data stores are built with high-performance NVMe devices. So if you have a lot of backup and archive data that will be infrequently accessed and that must be retained for a long period of time, it's probably more cost-effective to store this elsewhere. There are a few different ways to solve this challenge, but we're going to do this today with AWS File Gateway. AWS File Gateway is a hybrid storage solution that offers SMB or NFS-based access to the data in Amazon S3 with local caching. This means that the files are first cached locally on a dedicated virtual disk attached to the File Gateway VM, and then destaged to an Amazon S3 bucket, which is deployed in my AWS account. If you're unfamiliar with Amazon S3, it's an object storage service that offers industry-leading scalability, availability, security, and performance. It's designed for 11 nines of durability and stores data for millions of applications for companies all around the world. By default, S3 buckets are configured to only provide access to the account owner and root administrator, so what will create an AWS Identity and Access Management, or IAM role, and policy that grants our file gateway access to the S3 bucket. S3 buckets are also configured by default to block public access to the data, and I've reinforced this explicitly in the code. When the data is destaged from the file gateway cache to the S3 bucket, the data will be secured in transit via TLS. The NSXT Tier 0 router shown here is configured to route the S3 traffic over the private link interface instead of the internet. Setting can be found in the VMware Cloud on AWS Management Console. Once the traffic arrives at our VPC router, traffic is then routed to our S3 VPC gateway endpoint. For communicating privately with the S3 bucket, the VPC gateway endpoints influence traffic by injecting the necessary routes into our VPC route table. Once the data arrives at our S3 bucket, AWS File Gateway is designed to use S3 server-side encryption by default to encrypt the data at rest. Additionally, we're going to configure our AWS File Gateway to send its management and control plane traffic through a VPC interface endpoint instead of over the internet. VPC interface endpoints nav the traffic instead of routing it like VPC gateway endpoints. So now that we've described what we want the environment to look like, let's take a quick look at where we're at now and how we'll get there. The SDDC is already up and running and connected to our AWS account. When we start our build, Terraform will figure out which resources have dependencies, and then it'll start deploying resources with no dependencies in parallel. In this case, it's the MySQL Server VM, File Gateway VM, VPC Gateway endpoint for S3, and the S3 bucket. Once the File Gateway VM is online, Terraform will provision the IAM role and policy, as well as a security group that only permits connectivity from the AWS File Gateway's VM's IP address, followed by the VPC interface endpoint that will be secured with the new security group. After that, Terraform will activate the AWS File Gateway VM over our new private connectivity. Once activated, Terraform will configure the caching disk on the File Gateway VM and then create an NFS file share on our File Gateway VM that's backed by our S3 bucket with private connectivity. Last, Terraform will configure the MySQL Server VM to mount the new NFS file share, generate a database backup file, and save it to our new NFS mount. Once the AWS File Gateway VM receives the file, it'll cache it first, and then destage it to our S3 bucket for persistence. That's it. In testing, this whole solution typically takes less than 5 minutes to deploy. Before we kick it off, let's dive a little deeper on Terraform. Terraform config files are written in a language called HCL2, or HashiCorp Configuration Language version 2. HCL2 will soon be the default configuration language for HashiCorp Packer as well. If you're not familiar, Packer is another great tool that pairs well with Terraform. I covered this in my previous session, CODE4238, Building VM Templates Programmatically with Packer. If you missed it, the recording should be released soon, but check out the associated GitHub repository, and I hope that you'll build a few VM templates with it. That said, there are 7 key components to basic Terraform templates. Providers are just software plugins that tell Terraform how to interact with remote systems, such as vCenter and AWS. We're going to use 3 providers in our build today, which are the VMware vSphere, AWS, and null providers. There's a dedicated provider for VMware Cloud on AWS, but it's primarily used for spinning up software-defined data centers, or SDDCs, such as for a workshop. There's also a NSXT provider for managing your network and security policy, but we're just going to focus on building a workload today. When you want to deploy VMs with Terraform in VMware Cloud on AWS, you use the same vSphere provider that you use on premises. As you'd expect, We use the AWS provider for managing AWS resources that we'll deploy. The null provider is rather unusual though, because the resources intentionally do nothing. We'll create a resource with this at the end for launching a provisioner to configure our MySQL Server VM. Variables allow you to customize your build without changing the code. When you're doing this right, you can use the same set of config files to deploy your stack in both your dev test and production environments, and you only need to change the values of a few variables to do so successfully. Data sources are used to retrieve information about resources that this Terraform template doesn't manage. This could be a resource managed in another Terraform template, or the default data center object in vCenter. You can then use the information that these provide as inputs for components that you want to deploy. Resources are the most important because they're the virtual infrastructure components that you're going to deploy with the template. Provisioners allow you to make changes to resources after they're deployed. For the documentation, they should be considered a last resort and are not generally recommended because they add complexity, risk, and uncertainty. When you use these, you have to do stuff that you don't normally have to do, such as permitting direct network connectivity to the targets, providing credentials for Terraform to log in with, etc. Despite this, there are times when they're necessary, and I use one in the demo today to mount a NFS file share and to show you the data path. Ideally, you want to build immutable infrastructure and replace your resources whenever you need to make changes. Outputs are basically return values that are printed out at the end. Configure these to provide you with details about what you've deployed with Terraform. Terraform must store state about your managed infrastructure and configuration. The state is used by Terraform to map real-world resources to your configuration. We'll track our state in local files for our demo, but many people prefer to store state remotely for non-trivial deployments, such as in an Amazon DynamoDB table. Terraform will automatically detect any file with a .tf file extension in the working directory. However, a common design pattern is to organize your Terraform config files as such. Input variables are defined in a file named variables.tf. Outputs are defined in a file named outputs.tf. Almost everything else is stored in main.tf, such as the providers, resources, data sources, and local variables for your build. Last, I store the desired values for a few non-sensitive input variables in the terraform.tf vars file. Terraform will automatically detect this file and import the configured values when present in the working directory. Here are the 5 commands that you'll use 99% of the time. There are a few others that are really useful when you need them, but it should be pretty rare, so I'm skipping them in the interest of time. Terraform init initializes the working directory. Terraform validate checks to make sure that your config files are valid. Terraform plan, which generates an outputs and execution plan for the resources described in your config files. Terraform apply, which reruns the Terraform plan, generates the execution plan, but it also deploys and updates all the resources described in your config files. And last, Terraform destroy, which destroys all the managed resources that were previously deployed. Now let's kick off our build, as these will take a few minutes to run. So here's vCenter. First we'll run Terraform init. And I've already downloaded my providers, but this would have downloaded them if they hadn't already been. Terraform validate to make sure our config files are in a good state. Good to go. Terraform plan. And it's going to be hard to see because it generates a lot of output and not easy to see over a video. Normally, you'd want to review this carefully before moving to the next stage. Terraform apply. And again, that this reruns the plan job to generate the execution plan. And again, you'd want to review this carefully before proceeding, but I've done this a bunch. So now our build is running. Resources are being deployed in parallel as fast as that can be, as long as there's no dependencies. Our VM folder is already online. So are our 2 VMs. They're booting up, and they should have an IP address assigned soon. Our S3 bucket is created. And our 2 VPC endpoints have been created. The storage gateway via VPC endpoint is still in process of creation. The S3 VPC gateway endpoint is pretty fast. We're associating it with all of the route tables in the main route table. Or sorry, with all route tables in the VPC. And here's our new route that's injected, routing all the S3 traffic to our VPC endpoint. And our storage gateway hasn't started creating quite yet. So let's take a look at the code. Here's our variables.tf file. One thing I choose to do, and some others do, is I define my variables at the top that do not have default values. And then below that, optional variables that do have defaults. One nice thing about VMware Cloud on AWS is you can specify more defaults than usual, because there's some managed resources in there that you can just expect in every environment. Next, here's our main.tf file. So I start out with the providers, specifying which providers I want to use and the target versions for each, as well as the target version for Terraform itself. After that, I configure my AWS and vSphere providers. After that, I configure my local variables. Users cannot override or influence the local variables that are statically defined, such as the tags. So that's one common use case for local variables, or you can use it to format the user variables or input variables specified in the variables.tf, or format data sources or resource outputs or attributes. And that's what I'm doing here, is formatting resource attributes. And this also illustrates how Terraform maps dependencies. Even though I've defined a static setting right here, the static local variable, and a dynamic one that's not defined until later, until after the VM is created, Terraform's able to figure this out. And I can use my tags variable before these have even been defined. So after this, I define my data sources, which is mostly, for vSphere, is mostly just the resources I'm looking to use, such as the network and VM folder, sorry, create a VM folder, but the data center resource pool, all that good stuff. The 3 AWS data sources are a little bit more interesting. So I'm pulling in the route tables to the connected VPC, so that way I can inject that into the VPC gateway endpoint for updating, for injecting routes in all of the route tables. And here I pull in at the storage gateway local disk for our file gateway VM, and where we're looking for the secondary disk. And I use this to activate or configure the caching disk. And then for our storage gateway VPC endpoint, I determine the elastic network interface for it. So the ENI, and I retrieve the first object of all ENIs associated with that VPC interface endpoint. So that way I can get the IP address to use when configuring my file gateway. And so I can target it with IP instead of DNS. All right. And most of the resources are pretty standard fare, nothing too special about them. Except for this last one here that I mentioned before. Here's our null resource for configuring the NFS client on the MySQL server VM. We use an SSH connection. And here's our provisioner. So it'll create our mount directory and update the etcfs tab file. It'll mount our NFS file share and generate a MySQL dump file, so a backup of the MySQL server, and then output a success message. And here's our outputs. So this is the output that we want to see from our build, the interesting aspects and attributes of the resources that we've created. Let's see where we're at. Looks like it's all done. So here's our new file gateway. And here's our new file share. And oops. And here's our success message and the name of the file. Let's go back to our S3 bucket. And there's our file that's been destaged. All right. I'm happy to answer a few questions at this time.
If you have a question, feel free to put it in the chat. I think, let's see, feel free to also put it in the Q&A. We have about 1 or 2 minutes. If there aren't any questions, Troy will give you a minute back, give our attendees a minute back, and thanks for being on here.
Yeah, my pleasure. Oh, wait, here we go. Yes, D. So the source code is available. I updated the link in the details for the session. So, or you can scan the QR code there, but or just go to the URL listed on there. So it's under the AWS samples org. It's the VMware Cloud on AWS Web Workshops repository, and that there's a folder in there for it. So please do try it out, and reach out if you have any trouble with it or need help. But for everybody, thank you for joining today, and I hope you found this session valuable. Please remember to fill out the session survey afterwards. Thanks so much.
Thanks, everyone.